Hello everyone, my name is Callan Noak, and this is my project over the analysis of COVID-19 data using advanced machine learning models. So just a brief overview about what I'll talk about today. We're just going to go over the introduction to the project, cover the methodology that we used, go over the actual case study, and show our results, and then finish with our conclusions and future work. So to introduce our data, it was a public data set from Johns Hopkins University, so you can go there to their website now and actually pull this data for yourself. The time frame for what we got the data for was from January 23rd of 2020, so right near the beginning of the pandemic, to January 21st of 2022. So we're looking at roughly about 2 years worth of data. So our data specifically covers the number of daily new cases and daily new deaths due to COVID-19 in various countries. The data that we gathered covers over 196 different countries, so all different kinds of countries around the world that you can think of. And one last thing is we did clean and pre-process the data. The graph that I have over here on the right-hand side is not what you'll get if you go to the website yourself. It was actually split up to basically across different sections of the country. So like take the United States, for example. It was spread out based on states. So we kind of had to combine all of those into a single country because that's only what we're concerned about is the country data, not different regions or states or whatever it may be. Okay. So the first question we were asking is which countries should we model? With 196 different countries, we didn't have enough time to model every single one of them, so we had to make a decision on which one should we focus on. So we decided to come to the conclusion of we wanted to base our decision on the average daily cases and average daily deaths for each country. And so whenever we plotted that data, this is what we got here. And as you can see, the top three in both daily cases and daily deaths were USA, India, and Brazil. So we decided to go with those three, but we also did pick Iran as well as our fourth country just to get some extra data, so weren't focusing solely on the big three. We also wanted to get some smaller data as well, but Iran still is on both top 10 charts as well. So the methodology we used two algorithms. The first one is Holtz double exponential smoothing. So it's a variant of the normal exponential smoothing, where normal exponential smoothing, it takes basically its recency bias in the form of a mathematical equation. It takes previous data points and uses that to predict future data points. And so Holtz double exponential smoothing is an exponential smoothing equation that utilizes level and trend. So level is the value of the current data point that we're looking at, whatever it may be. And that equation is given here. So one thing to note in this equation is the variable alpha. So alpha is basically a weight that we assign each data point, and an alpha level close to 1 means we're going to assign pretty much a full weight to that, and an alpha level close to 0 means we're basically not going to take that point into consideration when we're designing our model. And then the trend is the difference between two previous levels. So basically two different data points. Is the data going up? Is it increasing or is it decreasing? What is the general trend that we're seeing from our data? And how much do we want to take that into consideration? So this is the trend equation, and similar to alpha, we have the variable beta, which is once again the weights. So if we do want to take a lot of the recency trend into account, we assign a beta level close to 1. But if we don't want to assign a very strong recency bias, then we set it equal to roughly 0. And then both alpha and beta are what we call the smoothing factors, so that's just another name for them. Okay, so then we combine the level and the trend to get our final forecasting equation, which you see here, and that's used to actually forecast the data. All right. Then the other algorithm that we used was autoregressive integrated moving averages, or ARIMA. So as the name implies, it integrates two different models, the autoregressive model and the moving average model. So in the equations I'm about to show you, just to give you all a heads up, P is going to be the order of autoregression, D is the degree of difference, and Q is the order of moving average. So covering just a bit of what these equations are, we started with the ARMA equation, which is basically D is equal to 0. This is more beneficial for stationary data, where it's basically not moving with time. And so we start off with this equation, and you can see that it has that order of autoregression and order of moving average. But then we wanted to simplify it, so we actually simplify it using the Box-Jenkins backshift operator. And this is just a simplification technique to make it a bit easier to read. But then we did want to introduce that differencing equation, which is basically just taking, kind of like with the Holtz double exponential smoothing, it's taking the differencing between two equations, and that's how you get this result over here. And we kind of combined everything all together and get this final forecasting equation. But you notice there is P, D, and Q. I didn't cover every single equation. There's a lot more than this, but I don't have time to really cover every single mathematical formula. So just know that this final equation is what we actually use to create our model. Right. So then going over our case studies, just a couple things to keep in mind when we're looking at these graphs. The black line, which you can kind of see in the background, that's the data that we use to actually create our models. The yellow lines are the prediction model, so that's what like our algorithms actually created these models to make them. And then in addition to predicting the data that we already had, we also wanted it to forecast 14 days into the future. And so that's what the red line represents. Red line represents the actual 14 days into the future of the data that we gathered. And then our yellow prediction model also tries and predicts what it has. So our main two goals here were to model the data that we did use to create the model. And for most cases, that was actually really good. But then we also tried to forecast 14 days into the future. And so not all of those are going to be perfect. It's just going to be, we're trying to basically either get the same general direction or within the same vicinity. If we can get both of those, great. If we only get one, that's also good. We're just trying to not get something where it's going in the completely opposite direction and it's also way different from the actual value. But how did we evaluate these models? We use these test statistics down here. The main one I'll be focusing on right now is R squared, just because that's a nice, easy number to focus on. We want an R squared value close to 1. That is going to represent a good model, good fit for our model. So right here I have is the US daily cases for Holtz double exponential smoothing and ARIMA, and they both have really high R squared values, so those are really good. And we can even see from the graphs, they even predicted the 14 days in the same direction. Okay. So then we have USA daily deaths. So once again, really good R squared value, 0.997 for both. And now here, even though they don't go up at quite the same rate, we're seeing they both go up. So once again, that's a good trend. Then for Brazil's daily cases, once again, really good R squared values of 0.97, 0.96, really good. And even if we didn't see them go up quite as much as the actual data, the general trend is correct, which is good for us. Daily deaths, we have really good R squared values, 0.999 for both. And here's a case where our model predicted they were going down, and it looks like they were going down in about the first week, but then the second week they started to peak back up, but they're still relatively in the same ballpark, so we're happy there. For India's daily cases, this actually has one of the best models, both 0.999 for the ARIMA model, and that graph is pretty much perfect. The red line and our model line up almost perfectly, so that's a really good model there. India daily deaths, once again, really good R squared values, and our graphs are still within the same general ballpark, so good there. Iran daily cases, also the same, 0.999, really good. And then for Iran daily deaths, once again, these models are actually really good as well. And then R squared value close to 1. Okay. So just go briefly over conclusions and future works. We were able to accurately model the number of COVID-19 cases for each chosen country. Awesome. We were able to accurately model the number of daily COVID-19 related deaths for each chosen country. Also good. So for our future works, we maybe want to try and shift our focus and try and predict smaller countries. All the three, as I mentioned in the beginning, we based it off of the highest average daily cases and daily deaths. So maybe now we're going to try and see if our methods will work on smaller data, countries that don't have quite as many cases or deaths. But then another thing we also want to try and introduce is introducing seasonal models. What we're noticing is basically COVID-19, the cases and deaths go up in the winter and they decrease in the summer. So introducing these seasonal models may actually make the forecasting element of each of these even better than the ones that we have there. All right. Thank you so much for taking the time to listen to me.